All right. Hi, everyone. Thank you for coming today. So today our speaker is Brad Rava. So he's a lecturer in business analytics in the business school at University of Sydney. He actually got his PhD from USC, and he's been working on statistics for societal problems like fairness and like fairness in AI and problems of like automated decision making and machine learning. And so today he's going to tell us about his work on fairness adjusted approach to classification. So yeah, Brad, it's all you now.
Great. Thank you very much for the introduction. Sort of on the outset, I don't know exactly how we want to do questions, but I'm happy to take questions as the talk goes on. Maybe if something's written in the chat, sometimes when I'm giving these Zoom presentations, it's harder to keep track of that. So if someone just can come off mute and let me know that there's something in the chat, that there's a question.
I'll let you know if there's anything in the chat.
Great, thank you very much. Maybe a little bit about my background. So I'm primarily a statistician, and I think my sort of introduction to this field of fairness maybe is a bit different than everyone else. So I'm happy to have like a bigger discussion about like maybe where this fits into some of the broader research that you guys have done. So I'm actually quite excited to and somewhat be presenting to this community, because it's not one I've actually had a lot of opportunity to do so. So the paper I'm talking about today is called "A Burden Shared is a Burden Half: Fairness Adjusted Approach to Classification." And really the question today, which it's not a question that's new for this audience, but how should we approach classification when our data contains protected groups, right? And as a statistician, we have a lot of tools for doing classification, but potentially we should do something a little more carefully if our data has protected groups. And in this case, when I say protected groups, I'm not really thinking of anything fancy. These protected groups are given to me, and I probably know them in the data. So there's nothing too clever going on with the protected groups at the moment for this paper. And I'd like to quickly mention my co-authors for this paper. So Professor Wen Sun at Zhejiang University, Professor Gareth James, who's actually the Dean of Emory Business School, and Professor Xin Tong at USC Marshall. So all co-authors on this paper. And before I really get into the paper, sorry, maybe we can. So before I go really into the meat of the paper,
Thursday you probably won't sleep very early.
Omar, I think you're unmuted.
Okay, so I think before I go into the paper, I'd like to talk about a problem I had during one of my internships in my PhD that gave me sort of different perspective on the problem that we're going to solve. And so I think typically when we think of fairness problems, we think of things like protected groups like race and gender, but I think this tool has like sort of a broad applicability. And so to sort of demonstrate that, I'd like to talk about this kind of general problem that I saw when I was interning at Google Maps. And so if you remember during COVID, Google Maps was actually becoming a little problematic. So you think about like the first couple of weeks or months when COVID started. And so what ended up happening on Google Maps, or I should say what ended up happening in the world, was that there was so much change going on that actually stores were closing very quickly. And primarily this is because we were not going out and going to these stores or restaurants on the map. And that actually became very problematic because stores around us started closing very quickly. Primarily like, let's say mom and pop restaurants, they weren't getting enough traffic, had to close. And that became a problem for Google Maps because stores were actually closing so quickly that we couldn't update the map fast enough to sort of keep track of these sorts of things. And that's a problem from a user experience standpoint, because we don't want to send someone to a store that the map says is open, but then maybe has closed down. And so that's not good just from a usability perspective. And so there was a lot of internal conversations about how we can potentially put a quick fix on this problem and do something clever. So the fix I'm going to mention was not used at any point. So I'm not really giving you any insight into what Google actually did, but I think it's a worthwhile conversation to sort of discuss. And so one simple fix that was discussed is that we put like stores on the map into 3 different groups. One group would be, we're really confident this store on the map is still open. One group would be, we're a little unsure if it's open, right? So you can go either way. And one group would be, we're really confident that the store is closed. And so if you could sort of put people into these classification groups, then what would you do as a data scientist or an engineer? Is potentially you would try to send people primarily to the stores that you're confident are open, right? And that hopefully would avoid any of these issues of sending people to stores that are closed. But there's sort of a little bit of a problem here. Maybe it's a problem that this audience picks up very quickly. When I give this talk to statisticians, not everyone really picks up on this problem. But the information we have on stores for Google Maps actually it's not all the same, right? So a good example is just think of coffee shops, right? So there's many different types of coffee shops in the US. One of them being Starbucks, which is very well manned, right? And potentially Starbucks' information on Google Maps is actually very good, because most likely someone at Starbucks is keeping track of the data that's being sent to Google. So a lot of the data that comes in is actually user inputted. So probably there's someone at Starbucks who makes sure that all the store hours are up to date. But then maybe if you have a local coffee shop, like the one I have here on the screenshot, like Cafe Dulce, which was a couple blocks off USC's campus, when I was doing my PhD there, there's only 2 locations of Cafe Dulce in Los Angeles. And so most likely they don't care as much about their Google Maps listing, or they're not keeping all this information up to date, let's say nearly as good as a big store like Starbucks would do. So if you were to do this classification scheme, right, without taking these differences into account, what would happen, probably on a very general level? Most likely what would happen is that we would send people to Starbucks, right? And I think that's probably not too hard to see why, at least at a high level, if you don't really take any of these differences into account. And it's because we have really good information on Starbucks, so we'll be really confident if Starbucks is open, right? But maybe we're Cafe Dulce, we're a little more unsure, or we're confident that's close. So that's a problem for a company like Google, right? Because we are dealing with tons of stores and tons of users, and we don't want to be excluding stores from the ranking or the list just because they're smaller or they're more, let's say, their data is not that good, right? And you can imagine that this would have very serious implications on small businesses if we were somehow unfairly penalizing them just because they didn't have the manpower to keep up with a store like Starbucks. And so that's kind of like some general inspiration, right? So I've not really said a problem yet, but maybe we have this sense that, okay, we have classification and we have maybe different types of groups, minority stores, right? Or larger, smaller stores, information disparity, things like this. And just to give us a sense of different ways to view this problem. And I think it's nice to think of this problem this way, because you sort of see that this fairness issue, I think, has broader implications than perhaps what we typically discuss. But generally, right, I'm just thinking of this like risk assessment software, like I think many of us already do. So we have some historical data, and this historical data is being pushed into some black box machine learning model. And for the sake of this talk, I'm really only interested in 3 classification groups. So like, high risk, medium risk, and low risk, right? Just like that Google Maps example. And this is really a chain here. And I believe everyone here in this talk can produce this chain up to some level of accuracy, right? And I always tell this to students, you should all be able to do this, if you're in a PhD program. And so I'm gonna use the classic example that I think most people in this talk have heard, which I'm gonna talk about recidivism. So let's say you're a budding data scientist that was hired to do this chain for risk assessments, and your client is the US court system, right? And they want to know which one of the defendants is at high risk of recommitting a crime so they can help set their bail. I'm going to move a little faster through this beginning motivation than I normally do, just because I believe that most people are very familiar with these examples. So using the latest and greatest machine learning things, you can take all that recidivism data and put people into these 3 classification groups. All right, and this is a very sensitive area. So what you do, right, is you could say, well, I'm going to make sure that the algorithm doesn't make too many mistakes. Right, and just for sake of example, I'm going to say, let's say you didn't want more than 25% of mistakes to be made. And I believe that most of you could do this. And there are a lot of algorithms that can do this very well. So you ensure that overall the error rate is at 75%. What's the issue with this? Well, the issue with this is if you were to break people into, if you were to look sort of deeper into that overall bucket, and you were to break it up by different protected groups, you would see that this rate of control is felt very differently between different protected groups. So that sort of hides the fairness issue. And really all I'm saying at this point, I've not pointed out a problem, I think, necessarily yet. I'm just saying that when we have sensitive applications, we should take a little more care into seeing where the mistakes are being made, and perhaps we can have a better handle on the uncertainty. And at least for me, I'm more interested in communicating this uncertainty back to the user so they can do something about it. And this can come through a classification, or it can come through an expression of doubts. And I think this is very important when we start to hit these more sensitive areas. I mentioned recidivism, but obviously, we can be talking about facial recognition. We could be talking about personalized medicine. We could be talking about things like the Apple credit card. all things that have been widely discussed, I believe, in the fairness literature, and all have profound implications. And these all generally have that same pipeline where you start from some risk assessment or some historical data, and you push it through some machine learning algorithm, and you want to make some classification groups to make a decision, right? Anyway, I'm moving a little faster through the motivation, but please stop me if I am moving a little too quickly. And so the whole point of this, as a statistician, right, is I want to express uncertainty better. That's really my end goal. And so we need to move beyond standard methods to make sure that if we make an automated decision, doesn't have unintended consequences. So as I said, if you want to control let's say the error rate of an algorithm overall, you might notice again that this is not felt the same way for all the different protected groups in your data. So what's our sort of role here? Well, I want to move us from this left plot to one on the right. And so what's the one on the right? And there's a lot more detail here than just a spot, but kind of in a general sense, if I give you some notion of error rate control, you want to know a couple of things. You want to know overall that it's at that level controlled, but also if you break it up by the protected groups that you gave me, it's also controlled at that level. And in some sense, we're pushing that budget as close as possible to that desired level that you told me, right? So, and so you would sort of see like an equalization of these error rates approximately. So doing this with real data, that's why there's a little bit of a gap there. And so the plot on the right is what I'm going to move us to in this talk, right? So we have this expression of uncertainty that is reflected across all the protected groups. And I want to do this in a way that is very friendly. And I think this is kind of the nice part about this presentation and the paper, is that I want to do this without requiring any restrictive assumptions, right? I don't want to say anything about the machine learning model you're giving me. In fact, I don't want to say anything about the accuracy of that machine learning model. And I want it to work for the data set that you give me. And so all these things are going to be taken into account, and we're going to move to that plot on the right in a really nice user-friendly way that I claim can essentially be applied to any problem you're currently using, and it's guaranteed to work. And so really quickly, there are a lot of fairness definitions that you can discuss, right? And I'm not claiming this is the best one, but I think you were getting the general sense of the fairness definition that I'm sort of pushing us towards for this talk, and that's the sufficiency principle. And so what is the sufficiency principle? It really just says we want to look at the cases that we've selected and then look at the rate of mistakes there, right? So we're conditioning on the fact that my algorithm has actually made a decision, and we want to effectively equalize this across protected groups. And this is a widely studied definition, and I believe most people in this audience probably have seen this before. But there are a couple of limitations from a statistician's point of view that I think are worthwhile addressing, and that I believe that we're able to address with this algorithm. So the first thing is this definition is primarily, the way it's defined, primarily focuses on making a decision for a single individual. But this is actually highly unrealistic in practical settings, because generally you're not making a decision for one person, but you're doing it for many people, right? And so in statistics, we would call this, an issue of multiplicity, right? Which is it's where when you make multiple decisions simultaneously, the error rate or the control that you have for one decision, that error sort of compounds over the multiple decisions. So you want to have a guarantee, not just on one decision that you're making, but on all the simultaneous decisions that you're making, right? So we need to take this multiplicity into account. And typically for the sufficiency principle, you cannot control the error rates always. And for this talk, and you'll see why we're able to do this, but I will offer control for any class and for any specified level of control. And then most algorithms that I've seen that satisfy the sufficiency principle generally are very computationally intensive and don't offer finite sample guarantees on the outputs of black box models. But we are going to offer something that's not computationally intensive at all. It's only as computationally intensive as the machine learning model you already were using. And we will offer finite sample guarantees, which is sort of the beauty of what this is offering, right? So I guess I said my guarantees a little too early, but we're going to ensure that the error rate, given a subject is classified, is going to be controlled below any user specified level. And so I just have an alpha C here because you potentially could have, if you have two classes, potentially you have different preferences for those. You could just think of it as some user specified level if you treat the classes as the same. And then to address multiplicity, we're going to introduce a new concept called the false selection rate, which we'll get into right after this. And this will allow us to say something about all the decisions we're making simultaneously. And then we're going to offer rigorous guarantees about the false selection rate control in finite samples, and we're not going to make any assumptions at all about the underlying model. And in fact, we're not going to make any assumptions about the accuracy of that model. So you, in some sense, could give me a machine learning model that was a random guess, and I claim that whatever I give you will still work. There's some caveats to that, which is that it's probably not going to be very powerful if it's a random guess, but it will still be fair by this definition. All right, so quick roadmap for the rest of the talk. I'm going to formulate a selective inference procedure for classification, and then I'll define that false selection rate for you, so we're all on the same page of what that means. And then really the key for this algorithm is I'm going to introduce something called the R value. And I claim if you understand the R value, you really understand the entire algorithm. But I'll show you the R value and the data-driven FASI algorithm that directly uses these R values for classification. And then we'll sketch the theoretical properties of the algorithm kind of very briefly, and some simulation and real data analysis. And I might move through some of these things a bit faster if I'm running out of time, but I think as long as we get to step 3, then I can at least mention the last 2 steps and then direct you to the paper after. Any questions up until this point? I've said quite a lot, so maybe I'll take a quick 5 seconds and see if everyone's on board. I have a sip of coffee. Okay, great. So let's keep going. So as a general setup, like every sort of machine learning talk you see, we have some data set D with some features X, but we have an additional feature that goes along with X called A. And A represents the protected attribute, which in this case is fully known. A lot of people like to think of A being inside of X, right? I'm just leaving it on the outside, so we're very specific about it. And our goal, at least for this talk, is to predict classes 1 and 2, which could be high and low risk for previously unseen observations. And we're going to focus on binary classification for this talk, but there are extensions to the multi-class case. And I actually think it's kind of an interesting discussion if you think about it very deeply. Let's say we're just focusing on binary. So if you think about it, right, if S is some risk score from your machine learning algorithm, then if S is extreme enough, you make a decision, right? And I think that's fair in sort of everything you've done. So if S is greater than some large threshold, which we'll call TU, then you classify them into class 2. If S is very small and it's less than some lower threshold, TL, you classify them to the first group. And this, if you write it like this, is already a selective inference procedure, right? And so why is this? This is because if S is extreme, so close to 1, if it's a probability, if it's close to 1 or close to 0, you make a decision. However, S could be not extreme enough to pass either threshold. And if that's the case, we return what's called an indecision, which means the algorithm, the FASI algorithm admits that it is not confident enough to make a decision, right? And so this diagram will show you exactly what I'm saying if you didn't understand. If the score is very small, you classify them as low risk. If it's very high, you classify them as high risk. Otherwise, you return this indecision, and you would do this for many observations, right? And sort of see where they land in comparison to these thresholds, right? And that would be, let's say, your classification scheme for properly chosen thresholds. And this indecision group really is one of the key points of this algorithm. And so we say observations that we're going to call in indecisions are ones that we cannot place into any one of the classes that we've defined, so class 1 or class 2, with enough confidence, right? So if we place you into a class, we're saying something very confident. And so if you're an indecision, that means we cannot classify you at this current time. And so what's the message here? I think the message actually is very nice for practitioners that really want to be careful. And the message is you should separately evaluate the indecisions. Perhaps this would be a great place to have human intervention. Maybe you should collect more data on these people, right? There are a lot of things we can do here. And I think this aligns with real policy objectives in the world, right? So, if you think about the recidivism example that I know we're all very familiar with, incorrectly classifying a low risk individual as a recidivist is a very costly error. Or maybe what should have happened was we should have collected more data on that person before implementing that machine learning algorithm, right? And maybe we could have that would have helped us avoid that decision. So while the indecisions are not necessarily costless, because we're dealing with high risk decisions, they certainly are a much better alternative than forcing an automated decision on observations that we're not confident enough in. Oops. Did I go the right way? There we go. All right, so now I'm going to define this false selection rate. So what we want to control is this rate of erroneous selection. So given that I've selected you, we want to make sure that some proportion of these people were not incorrectly placed into that selection group, right? And that really is just the expected number of misclassifications, over the number of selections, right? So it's just a rate given I've selected you. And if you want to focus on a particular class, we could define this false selection rate, for that specific class, right? So this is the same quantity. However, now we're just focusing, let's say, for example, on the high risk group, right? So the number of truly low risk individuals that you thought were high risk over all your high risk selections. Well, we have to go one step further because this is a fairness talk. And so we don't just want to control the false selection rate, but we want to control the group-wise false selection rates. And that means we want to look at the previous, let's say, high-risk false selection rate for every protected group. And this is the quantity that you want to make sure is controlled below a user specified level. So you give me some level, and we want to make sure, and that could be 5%, 1%, 2%, and we'll make sure that this quantity is rigorously controlled at that level. And so this is the false selection rate, which is the key quantity that we want to control here. And you can already see why this addresses multiplicity, right? Because this is a statement about all the decisions that you've made, right? So that's how we're able to focus on that issue. And obviously, if you wanted to talk about the low risk group, you could redefine this false selection rate in the same exact way. And the indecision group is very important, and the indecision group is going to reflect the concept of power, right? So typically, we want to have some sort of fairness control, and then you want to talk about power. So in this case, we can define power as really the size of the indecision group, right? So our goal here is to make sure that that false selection rate is controlled, but also that we're not making too many indecisions, right? And obviously, some indecisions are going to be unavoidable if you want to have exact control over the false selection rate for each class. But given that it is controlled, you would prefer the scheme, right, that made as little indecisions as possible. So you're making as many actual classifications as you can, given that false selection rates constraints, or the group-wise false selection rate constraints. And so we define this as the EPI, or the expected proportion of indecisions. Oops, sorry, skip that. Okay, so what makes a fair classifier, right? And so this is sort of going to be key into how we're developing the FAST algorithm. So let's think of a simple thresholding rule, right, where we have some score again, and we check if it's more extreme than some threshold, and if it is, we put them in the class 2. And so in the way this is written, right, and this won't be a surprise, I think, to most of the audience here, we're using a single threshold to try to do some fair classification, right? And using the same thresholds for everyone, in some sense, will inevitably lead to unfair decisions. Right, where S here is some risk metric. And so to see this, I'm going to construct this very idealized Oracle setting and show you a really quick simulation to show why this won't work. So there's sort of 2 approaches you could do if you adapt this universal thresholding scheme. And the first thing you could do is look at something called the full covariate classifier, or the FCC, right? Just as we call it, all right? And if you look at that scheme, really the only thing you have control over is how you construct S. And so you potentially can construct this score with all the information in your data. Just give it everything, right? And then pick a universal threshold. Or you can construct that score excluding the protected attribute. And if you do that, we'll call this the reduced covariate classifier. And because they're using a universal threshold, it doesn't matter really how you construct that score, they're both unable to control the false selection rate. And this should be surprising because the simulation I'm showing below is actually done in a fully Oracle setting. So I'm going to calculate scores to be threshold that are exact posterior probabilities of classification, right? So I know the true underlying data distribution, and so I can construct those exact scores. And you can see if you use a universal threshold in these plots below, both the FCC and the RCC are unable to control the group-wise false selection rate. So if you see the purple line, that's for example, I use males and females as a protected group, but this is purely simulation. And let's say you want to control the false selection rate at 10%. You could see that overall, both methods are able to exactly control that false selection rate. However, once you break it up by the 2 protected groups, it's unable to do this. And so the y-axis here is that false selection rate, and the x-axis is the proportion of signal from the female group, right? And so you can vary that signal from 0 to 1, right? And that would mean 1 would mean everyone in the data set truly belongs in that class, and 0 means none of them do, right? And you just vary that single proportion, and the proportion of males was fixed here just to be 50% as an example. And you can see in this Oracle setting where I'm using all the information about the underlying data distribution, both the FCC and the RCC are unable to control that group-wise false selection rate. And that's sort of like a key thing to understand and why you can't use a universal threshold in this setting. So how are we gonna equalize false selection rates then? Well, what we could do is we could use the original base scores and set varying group-wise thresholds. That would work. Or we can take the approach of this paper, which is we can actually construct new scores. And these new scores will basically be adjustments of the base scores coming out of your machine learning algorithm. And they're going to have an interpretation that can essentially go across all protected groups. So you only need one score, and then you can use a single threshold for that single score. And you'll see what that is. That's going to be the R value metric I mentioned earlier. The reason why we don't want to use approach 1 is because it's kind of confusing and controversial if you start setting all these group-wise thresholds. And so we want to move, at least if we can, towards a method that uses a single threshold, but then the metric that we're using has an interpretation across protected groups. So you can actually apply a universal threshold in that case. And so we're going to go with this approach 2 because implementation is straightforward and interpretation is easy. Right, and so our method FASI, and I think I've said FASI a couple times, but I never actually defined it, as my apologies. FASI is going to be fairness adjusted selective inference. It's going to, in this same Oracle setting, is going to be able to do what the FCC and the RCC could not, right? And it's going to be able to effectively equalize all of the rates of erroneous decisions. So overall, for the females and males, and individually for female and male, for all values of PF, so the proportion of females, right? And this is exactly what we want to get to. Exactly at 10%, exactly equal, perfect. So we develop a fairness adjusted selective inference framework called FASI, and FASI creates an R value, which effectively equalizes the group-wise false selection rate. And again, it has an interpretation that is comparable across protected groups. So if you threshold an R value, which we'll define a little bit later, to keep you in suspense, then this leads us to false selection rates that are fair. All right, so what is the FASI algorithm? So I'm going to explain to you the algorithm as if you already knew what the R value was, and then I'll tell you what the R value is. But really, the FASI algorithm, it's not as complicated as you would think. So really, what we first do is you look at your historical data set D, right? It's some data set of historical observations, and it has some results in there. And you're going to take this data set and you're going to split it into a training data set and calibration data set. And then let's say you have some new observations in a test data set that you actually want to make decisions on, right? And you don't know the results of the test data set, right? If you did, then this problem would be given away. So you have some new observations in the test data you want to classify, and then you have a training and calibration data sets, and that can come from some data splitting. So the first thing you do is you tell me, what do you want to control your group-wise false selection rate at, right? And that's a user specified level, so that's up to your preference, and that really depends on your level of risk for the given classification scheme. And so step 1 is you take the training data set and you use your favorite machine learning model. And you don't tell me what it is, because again, it doesn't matter, right? But you use your favorite machine learning model, the most complicated neural network going on at your company, and you train a score function. And then step 2, you calibrate this R value for every individual in D-test. Then step 3, once you have that R value, making decisions is very, very easy. You just compare that R value to alpha, that user-specified group-wise false selection rate, right? And that's exactly how you make the decision. So if the high-risk R value is less than alpha, then you can classify that as high risk. If the high-risk R value, if the low-risk R value is less than alpha, then you classify that as low risk. And that's it, right? It's a very easy thresholding rule once you have that R value. So it's very easy for practitioners to use this. And I know that reading an algorithm like this can be very confusing, which is why I made this nicer animation to better communicate exactly what we're doing. So we start off with some observed data set, right? And then we have some test data sets on the right that we actually want to make decisions on. And for the sake of example, let's say you have two protected groups here, the green protected group and the blue protected group. And let's say we'll start off by making decisions for the high risk classification group. So the first thing you do is you split this observed data into training and calibration. Boom, easy, split it. Step two, you pick your favorite classifier. Again, I don't need to know what it is, but just pick your favorite one and train it on the training data sets. There it is. That's your favorite machine learning algorithm. And now I need a base score. So predict a score. It's a ranking score, right? As long as it's a ranking score, we're good to go. But typically people think of these things as posterior probabilities of classification, right? And this can come from really almost any machine learning model. And give me that score for everyone in calibration and everyone in tests. You can make that prediction. And step three, you use both the calibration and the test data to calibrate this R value, right? So boom, now you have R values for the test data. And once you have these R values, you just threshold, right? So if I say alpha is 5%, right, then I look at all the R values, less than 5%, boom, those are my high risk individuals. And then I fully repeat the process for the low risk group. And then everyone left over becomes the indecisions, right? And those are the people, right, where after I look through every classification group with the R values, I couldn't place them into either of those groups with enough confidence. So if they were to go into the groups, then we would know that one of the false selection rates would be violated, right? Then you would not have exact control. So that's why they're not being placed in there. So that's the interpretation of the indecision group. Okay, so what is this R value? Right, it seems like everything really hinges on this R value, and understanding it's actually not as complicated as you would think. So to obtain the R value, you first need, as I said, a risk score for every individual in the calibration and the test data sets. So when you calibrate this R value, let's say you have one for a single individual, right? So you can pretend it's me or you. Let's say I'm at you, and this is a general you for anyone in the audience. Let's say I stop at you with the FASI algorithm. And I ask myself, what is your R value? And so I look at your base score, and let's say that score is little s, just for example. And then I ask myself, if I were to put a threshold at you, if I were to stop at you and make you the decision boundary, right, what would be my estimate of that false selection rate? And that's effectively exactly what this R value is saying. So if you look, it looks very complicated when you first look at this, right? But then actually, if you think again, it's not that bad. So the numerator is basically saying, well, if I stop at you, right, and your score is little s, how many violations do I think I would have, right? And I can actually count that in the calibration data sets, right? And I can count that in the calibration data set because it's a historical data set with labels, right? And then in the denominator, right, I'm counting the number of selections, right? So I say, if I stop at you, how many selections would I get, right? And that is the R value, right? I'm exploiting a mirroring process here, right? So the calibration data set actually can be used to estimate the number of violations, even though you don't have that in the test data. And then at the very end, I adjust for potential unequal sample sizes between the calibration and test data set. That's what those leading fractions are on the front. But really all you have to understand, I think for the purposes of this talk, is the interpretation of the numerator and the denominator. And the R value, it's a really nice quantity. It's a fraction between 0 and 1. And FSR analysis is very straightforward once you have it, because you only need to compare that R value to alpha. And you specified alpha. So it's very easy. It's a sort of thresholding rule. I think that's very simple to implement. And the R value has the following interpretation. So if you make a cut at any R value, so if you get all your R values and you say, I'm going to stop at this R value, I'm going to slice here, this is where my decision boundary is. Let's say you're doing this for the high risk group, then you expect approximately for every protected group, 100% times R of the selected cases don't belong in there, right? And I think that's very natural when you care about false selection rates. Okay, so there's no completely free lunch, right? I said we're gonna do this without any assumptions. I do need one assumption to get this to go through, and that's the calibration and testing data set are exchangeable. And so why does this work? So for simplicity, if you think about this thresholding rule, right? Really what we care about
sorry,
is...
super quick question. What do you mean by exchangeable in this case?
So exchangeability just means if I were to take observations and permute the ordering, the distribution would not change, So really what this means, like if you think of it like simply, right? Like if I take an observation, I can't really tell if it's from the calibration or test data set. So you can move them around and you really wouldn't be able to tell the difference. I think that's the easiest way to think about it.
Right, that makes sense. Okay, yeah, thank you.
Welcome. So why does this algorithm work? And I think a simple explanation is to think about what you want to calculate sort of in an idealized setting. Ideally, actually, you don't want to calculate that false selection rate. You want to calculate the false selection proportion exactly on that test data set. And so what is that? That means if you were God, right, you would go to the test data set and you would actually count the number of violations. Right? If you knew why, then that numerator wouldn't be some fancy calibration sum. It would be counting the actual number of violations at that threshold. Right? So if I stopped at you, again, general you for everyone in the audience, if I stopped at your base score from the machine learning algorithm, if you had full knowledge of y in the test data, you would just count the number of violations up to that point. And that would be your numerator, and the denominator, again, would be the exact number of selections. So this, in some sense, is the oracle quantity, right? So this is exactly what you want to calculate. But what's the issue? Well, the issue I've already mentioned, right? And that's you don't have the labels y in the test data sets. And in fact, if you had y, you probably should just use those directly, right? However, we can do something a little clever. We have exchangeability, as I said, right? So because we have exchangeability, then the unobserved process in the numerator can actually be strongly resembled by its mirroring process in the calibration data. So instead of counting in the test data, you count in the calibration data, right? And then we finish by adjusting for potential unequal sample sizes. And really, I think the key of this paper, I think it's a couple of things, but showing that this works, I think, is really is a really novel part of the paper. And I think it's very intuitive when you see it, but showing that it works is, I think it's very nice. So for a lot of you who want to go into the paper, it's a nice argument. And if you were to do this, then if you stop at the R values and threshold them, you follow the FASI algorithm, then you know that the false selection rate is controlled for every protected group up to some constant gamma. And this gamma is really just the difference between the proportion of individuals that don't belong to class C in the calibration and test data. Because we assumed exchangeability, that gamma should be nearly 1. But potentially, if you think about some extensions, and I know a student actually who's thinking about this very deeply, you can do something about that gamma. But because we have exchangeability, and we have some simulations to show this, in practice, this is almost nearly exactly 1. So you have essentially exact control over the false selection rates. Yeah, so under exchangeability, gamma can be close to 1. Just to really quickly just mention some of the theory, but there are a lot of challenges with this. So I know I kind of make it seem like things are very simple and we just split a mirroring process. But again, I said you could do this for any machine learning algorithm, right? So the theory has to know how to handle the unknown and complex dependence between the base scores. I don't have any theoretical knowledge of how these things are generated, so I have to evaluate the false selection rate without assuming anything about how those scores got there. And these guarantees are non-asymptotic. They're finite sample guarantees. So you know that it's going to work for the data set at hand. Yeah, I say sorry. I'm kind of repeating myself at this point, but we have no assumptions on the underlying models or qualities of the scores. And so as you can imagine, right, I said you can give me a random algorithm, and I stand by that, right? So if you, let's say, we're not a good data scientist, and instead of doing a neural network, you got a coin and you flip the coin for every single individual, I claim that actually the FASI algorithm will still result in fair scores. However, most likely what's going to happen if you don't have very good scores is that you're going to be pushing more people into that indecision group, right? And so having a bad algorithm means that you're going to make a lot less decisions, right? So it's to your advantage to pick an algorithm that gives you a better score, but you will always be fair, right? Which maybe for some of us who have worked with a lot of students or had colleagues we've maybe not been very fond of, this is a great message to send. Yeah, controls exactly finite samples. And so what does the optimality sort of in this paper sort of tell us? It actually tells us something very interesting about the way the score needs to be constructed for this algorithm. And you actually want to use as much information as possible to estimate this score. And so you want to use the protected group in the machine learning algorithm. So don't deny the machine learning algorithm, at least for the purposes of FASI, knowledge of that protected group. because you're going to adjust for the protected groups in the calibration stage. So the message here is that if you don't use the protected group in the training stage, your score typically is a little suboptimal. So you'll probably make more indecisions. And so you shouldn't adjust for fairness in the training stage, but you should adjust for it in the calibration stage, where you have the R value and you let the R value sort of adjust for these disparities in the error rates. So at least for the purposes of this algorithm, that it would be the optimal thing to do in terms of minimizing indecisions, right? And that's sort of this, but the Oracle FASI procedure, so if you, basically what this tells us is if you had those exact posterior probabilities, so these scores here, if you had the Oracle posterior probabilities, that condition on A, right, to the protected group, then you would minimize the total number of indecisions. So your machine learning model, the goal really is to get a score or ranking score as close as possible to that exact posterior probability. And that would minimize the number of indecisions that you're making and also exhaust the power, right? So that's why, like, when you say alpha, you give me an alpha you want to control it at, you want to get as close to that budget as possible. And that's what the FASI algorithm is able to do for us, get us as close to that budget. There are a couple of algorithms I wanted to quickly discuss. I guess actually there's not a lot of algorithms that exactly do what we want to do. And that's really the message here, but there's a lot of really interesting work that's done in this space, but a lot of them don't offer the same finite sample control or minimal assumptions on the model accuracy or anything like that. So I think we really do stand independently here. But I don't mean to show the other slide. I'm always very hesitant to show competing methods because I think those are bad algorithms. They're sort of done in very different settings, I think. And so it's, I think they're all very, very, very good works in that setting. So let me look at time and see. I have some simulations to show.
You can probably take more, like 5 more minutes.
5 minutes?
Yeah, 5 minutes.
Okay, well, for the simulations, maybe I'll quickly kind of brush over these because simulations always look good if you follow most talks. But in the simulations, I compare FASI to the full covariate classifier because if we look at the reduced covariate classifier, it sort of always does worse because of that optimality theory I showed you. And so for an example, I generated some risk scores using a GAM classifier, just kind of sort of randomly. You can pick any classifier you wanted. And then I generated data from a mixture distribution of 2 protected groups, male and female, right? And then if you see pi on the next slide, pi CA, that's the probability of belonging to class C, given your protected attribute. And we fixed the proportion of males and females to be 50%. So there's no sort of disparity in the protected group proportions at the moment. And let's say the goal is to control the false selection rate at 10%. And if you do this, you can sort of see in this plot in 2 different settings. So in one setting, I generated exact posterior probabilities because I knew the underlying data distribution. And in one setting, I used GAM to estimate those posterior probabilities, right? Those ranking scores. And you can see here that FASI, which is the purple line, is effectively able to equalize that false selection rate, and the full covariate classifier is not able to. And the plots on the right are sort of showing the expected proportion of indecisions. And we don't lose much in this setting, at least, in terms of the number of decisions making between these 2 procedures. And that constant term in front of the false selection rate control, as I said, in simulation, it's guaranteed. It's exactly 1 here. So you have exact control for the false selection rate. And then I also went back to the compass recidivism example that I think we're all very familiar with. And I'm able to, again, use the full covariate classifier to make decisions and then use FASI to also make decisions. So in this case, the y-axis is that false selection rate control for the high-risk group minus whatever user-specified level you gave me. And that means we could just look at the difference between 0. But really, you can just think of the y-axis as the false selection rate, but sort of tilted, so it's a straight line. And the x-axis is that false selection rate control alpha. And if you do this, you see that FASI is able to, again, effectively equalize the false selection rate for any alpha that you give me, which is very nice, but the full covariate classifier cannot do this. And again, in this case, the difference between the proportion of indecisions between the full covariate classifier and FASI is minimal. It's very, very small, which is a nice message, at least in this specific setting. Okay, so just to really finish up, I want to hammer a couple of things home. So the FASI algorithm, again, effectively ensures what? It effectively ensures that the probability of misclassification, given that I've made a decision on you, right? So we're only making guarantees on people that we're making decisions for, right? So it's a selective inference procedure. and we ensure that that is threshold by alpha, by some user specified of alpha across all protected groups. It's referred to, it's similar. It's not exactly the same, right? But it's similar to the sufficiency principle. And the FASI algorithm can be thought of sort of at a high level as a calibration by group approach. But I think our work sort of departs from the existing machine learning literature in a lot of ways. One, I think FASI is very easy to compute, right? I've not shown you anything computationally very intensive. So you're not really going to lose any overhead here in whatever procedure. And a lot of methods that I've seen are very computationally intensive. Right? We're not asking you to do anything like that. And FASI works for any black box machine learning model and requires no accuracy on the outputs. And a lot of existing methods don't offer statistical guarantees on the error rate control and don't discuss what happens when you need to classify multiple individuals, right? And so we're able to do this here because we deal with the false selection rate and we offer exact control in finite samples. And so I think it's a very nice sort of, I think, addition into the space, or another way to view the problem, at least. And the conclusion, sort of again, me just trying to reiterate all these main points, again, works with any black box classifier, requires no assumptions on the accuracy of your model. And right, if you give me a classifier that's not very good, you'll probably just make more indecisions. We effectively control the group-wise false selection rate. And I think the nicest message really about this algorithm is we are directing the user to individuals that potentially they could focus their energies on, right? And we're identifying people that they should not make a decision on at the moment. And I think we've done it in a very clean way. So the interpretation of that indecision group is very obvious. And I think will allow better decision-making in high-risk classification schemes, because we've identified these people and we potentially do something about it, which I think is quite nice. So this all comes back to that message of communicating uncertainty better to the person who's using the algorithm. I think that's the main goal of this procedure, is to help a data scientist or a user who's dealing with a very abstract problem that they perhaps cannot understand and perhaps cannot theoretically understand, because it's a very complicated procedure, but it's allowing them to get a handle of this fairness problem and do something about it, at least at a basic level. And that's where we're at. So thank you very much. I'll stop here and I'm happy to take questions.
Yeah, thanks a lot, Brad, for the great talk. Yeah, if anyone has questions, now's the time. We have like about 5-6 minutes for our questions right now.
Maybe the talk was too clear. No questions.
I mean, I think the talk was very clear, so yeah. I think I already asked you the questions that I had last time we chatted, so I don't have any right now, but yeah. All right, then I guess like if no one has questions, I think we can end the talk here. So like let's thank Brad again. Yeah, thank you very much, Brad.
Thank you very much for the opportunity to share my work with you guys.